Hello, everybody, and welcome to my astronomy class. I am Dr. Lindsay. I am going to be your instructor slash guide through going through astronomy this semester. Fall 2020, as everybody is very well aware, is a strange semester. It's definitely strange for me. This is going to be the first time I have ever done a fully online course, much less a fully online asynchronous course, which means that we don't have a scheduled meeting time. Instead, I've put together a semester schedule, and we'll have week-to-week tasks that you'll work through. I will interact with you via Canvas discussions, and I'll be releasing videos like this one out to you throughout the semester. I highly encourage you to make use of Canvas to communicate with me. This is going to be for discussions or any other sorts of issues that you might have. It's where I will hub all of our materials from. Other than a few Google Docs and things like that, I do not expect to be sending you to any other platforms. Just keep everything at home in Canvas. So later on today, I'm going to be releasing a series of videos that will walk you through kind of how the class will be structured, sort of a video tutorial of the syllabus. But for now, I want to make this first video a welcome video, introduce who I am to you, and do a little bit of a mini lecture that I hope is a little bit mind expanding to get you excited about astronomy. So let's go ahead and start with who I am, Dr. Lindsay. And now you get to see how well I can share screens. I promise you I'll have plenty of issues with it throughout the semester to make sure everything works. All right, I have my slides here. It looks like I might be good to go. All right, so who is your instructor? This is a little bit of a chance to let you know who I am, toot my own horn a little bit, and hopefully convince you that I am qualified to be your astronomy instructor. So I am a local. I'm guessing most of you are here in Knoxville. I am from Maryville, Tennessee. I grew up there. I went to Maryville High School. And from Maryville High School, I then came to the University of Tennessee. While at the University of Tennessee, I had a lot of trouble making up my mind exactly what I wanted to do, but I ended up getting a bachelor's in physics and a separate bachelor's in mathematics. So I got two different bachelor's degrees, and I ended up going into astronomy. Is why I finished out my physics degree, and why I wanted to add mathematics to my education as well, because I became very, very interested and wanted to become an astronomer by actually taking the very class that you are right now. It was way back when, I won't tell you how long ago, but I took intro astronomy courses, the one that you're in right now, or at least a version of it, became enamored with astronomy, and since then I have basically been directing my education and my goals to being able to make these videos for you and be your astronomy instructor. After I got my bachelor's degrees, I moved on to graduate school because yes, a career in astronomy does require grad work or a career as an astronomer. There are lots of careers in astronomy. Not all require higher post-grad education. But I went to New Mexico State University to do my master's and PhD in astronomy. While I was there, in my second year, I wrote a proposal to become a graduate student researching fellow with the NASA Ames Research Center. That proposal was accepted, so NASA ended up funding my dissertation research. So I split earning my PhD between New Mexico State University and the NASA Ames Research Center. After I achieved my master's and my PhD, I went to work as a researching astronomer out in the world just as a scientist. I initially moved back to Knoxville, where I worked in the Earth and Planetary Sciences Department as a planetary astronomer for 2 years. I then took a second post at the University of Oxford, not the one in Mississippi, the one across the Atlantic in the UK, where I was working in their physics department, working on some new radiative transfer code to try to understand how light escapes and interacts with asteroid surfaces and comet surfaces so we can figure out what they're made out of. After those 3 years, I found an opportunity to return back to the University of Tennessee and back to Knoxville. There was a position for the University of Tennessee Astronomy Coordinator, which is my current position in the department, which means I'm in charge of the undergraduate curriculum. I manage all of our undergraduate laboratories, and I get to lecture all the wonderful introductory astronomy courses, the one that you're in right now. This is my 6th year as the astronomy coordinator, and I'm loving it so far. This is going to be a wild adventure of doing things online. So for the remainder of this video, I'm hoping this can be a little bit interactive. I want to do a little mini lesson about our place in the universe. I do a little bit of a scaling exercise to figure out exactly where we are and how enormous the universe that we live in is. And hopefully you can find the universe is absolutely fascinating, and we live in just this little tiny corner of it that we call Earth. So there are lots of things that make up our universe. Of course, there's space itself, then you have to talk about time, and then the matter and the energy of the universe. But what kind of objects are in the universe? We have everything from the small to big, and that's what this is showing here, from the Earth, and we live in a solar system. And then our solar system is in this neighborhood of stars, and the neighborhood of stars exists in our home galaxy, the Milky Way, which is part of a group of galaxies, which is a part of a supercluster of galaxies, which is a network of superclusters that make up our entire observable universe. Yeah, I did just cover the entire scale of the universe in a couple of minutes. So I said I wanted this to be interactive. So what I'm going to ask you to do, there are going to be questions that I have up on the slides as I go through this video. When you access the link to this video, there will also be a link to a Google form where you can supply your answers to the questions. There are no right or wrong answers. This is not graded, it's not even mandatory. It's just a way for you to get a little bit of interaction in this asynchronous, non-interactive environment. I don't know how often I'll employ this device. I had this idea literally about 30 minutes before I started to film this video. So let's see how it goes. Make sure that you click on the link, and when you get to a question, I'll prompt you to pause the video, and I'll pause a little bit myself and go ahead and answer the question. And hopefully that'll make this long video feel a little bit shorter since it's kind of interactive. Normally I'm going to keep my videos to be at the 10 to 20 minute mark. I occasionally might have a 30-minute video if it's a really, really interesting topic. All right, so let's jump in. For this exercise, we are going to have to put on our imagination caps. You're going to have to really try to picture something. A lot of astronomy is basically a visual spatial exercise. One of the best ways that we can actually start talking about the grand scales of the universe, or even our solar system, are through scaling exercises. And that's where we will imagine something scaled to the size of something else. For this scaling exercise, I want you to picture Neyland Stadium. Hopefully it will not look like this fall, if football will even happen. We need to remain socially distanced, but here is Neyland Stadium. Many of you have probably seen it on TV. Many of you have also probably seen it in person, so this is hopefully a good thing for you to picture. So now that you have Neyland Stadium pictured in your brain, what I want you to do is imagine our entire solar system. Let's put the sun at one end and then start going out past Mercury, Venus, Earth, Mars, Jupiter, Saturn, Neptune, Uranus, and you could keep going all the way out into the Kuiper Belt where Pluto is, so on and so forth. But we need sort of boundaries here, so I want you to picture all of the planets. The sun all the way out to Neptune, and let's start squeezing that down smaller and smaller and smaller and smaller and smaller and smaller until it would fit on the football field inside Neyland Stadium. We will put the sun at one end zone and Neptune, the farthest planet away, at about 30 astronomical units, 30 times farther away from the sun than the Earth is, at the other end zone. So that gives us 100 yards between the sun and Neptune. That's our scale. All right, so can everybody picture squeezing the solar system down to fit in a football field? If you can't, that's fine. When we're actually squeezing this down, not only are we squeezing the distances, but we're also making the sun smaller and smaller and smaller, so everything is scaled to size. The Earth, Jupiter, and everything is shrinking down in size. Which brings me to our first questions. And if you want to, you can discuss this with a friend, but this is where I'm going to ask you to pause the video after these questions, go to the Google form and answer questions 1 through 3 on the Google form. They should match these questions right here. So on this scale, normally I have you discuss this with your neighbor. Instead, you're going to be discussing it with the Google form and interacting with me that way. A little less interactive, but hopefully still fun. On the scale, I want you to take your best guess of how big you think the sun is. What does it actually scale down to? What size? On this scale, how big is the Earth? On the scale, if the solar system with the sun at the 0-yard line and Neptune at 100 yards away was our solar system, where would I put the Earth? Where on the football field, what yard line would it fall on? Now, this is a really, really difficult question, so I should give you some prompts. And that's what this slide right here is all about. These are the choices that you'll find on the Google form, and it's at the end of this slide that I am going to ask you to pause. So, the correct answer for the size of the sun and the size of the Earth is on this list. The sun is one, the Earth is another. They're not the same thing. So, what are your choices? The size of a typical house, the size of a typical dorm room, the size of me, Dr. Lindsay, human-sized. I have this styrofoam cooler right here, so you can actually see how big it is. So the size of the styrofoam cooler, it's just shy of 2 feet across. The size of a basketball, and who would have guessed that an astronomy professor doesn't have a basketball at their home? So instead, the size of a Frisbee. They're about the same size. The size of a baseball. Again, I don't have a baseball sitting around, but I do have a disc, a wooden disc, that is about the size of a baseball. The size of a golf ball. The size of a quarter. The size of a coffee bean, perhaps my favorite of all the beans. Now we're going to get to some of the really, really small things. Here I just have a regular pin, so the size of a pinhead. The size of a grain of, let's see if I can actually show this without ruining my computer, a grain of salt. So yes, just little grains of salt here. The size of a grain of flour. I'm not providing an example here because I do not want flour all over my living room. Or the size of an atom. So how large is the sun? Which item would the sun be? Which item would the Earth be? And then that third question, on what yard line would you find the Earth? So go ahead and hit pause on the video. Fill out those answers on the Google form. Don't submit it yet because there's still a few more questions. And don't go back and change your answers. Remember, there's no right or wrong answers. This is not supposed to be intuitive. A lot of the size scale stuff about the universe is not exactly intuitive. But it is a fun little exercise that we can all participate in. And I'm very interested in seeing what kind of perceptions people have. When I first did this, I'll be honest, I was way off. I was surprised, as I hope that you all were. So go ahead and hit pause, and I'll pause myself for a second. I think I blinked, so I wasn't super paused. And let's go ahead and move on. All right, so you've gone and you've made your choices. So on this scale, the sun is the size of a quarter. So in Neyland Stadium, at the 0-yard line, I would put a quarter, and that would represent the sun. Wow. Imagine you're up here in the stands. Do you think you could see a quarter down on the football field? I probably couldn't. And that's the sun, the star of our solar system. What about the planets? What about the Earth? So I didn't ask you about this one, but just to sort of give you some foreshadowing, the pinhead is about the right size for the largest planets in our solar system, Jupiter and Saturn. And Jupiter, the largest of all the planets, is so large that you could add up the mass of every other planet in our solar system, and Jupiter is still 2.5 times more massive than that. And it's just a pinhead in size down on the football field. So where does this leave the Earth? And now you're wondering about your guesses. The Earth and the other terrestrial planets, or at least Venus and maybe a little bit too big for Mars, is a grain of salt scaled to be on the football field. Holy crap. I definitely couldn't see a grain of salt down on the football field, even if it was a nice smooth surface so it wouldn't get lost in the weeds. And then the smallest things in our solar system, so the Kuiper Belt objects like Pluto, the smallest planet Mercury, the biggest asteroids in the asteroid belt, would be best represented by grains of flour scattered on the football field. The solar system is an enormous place, and the things that are in the solar system are incredibly small. Our sun, which is 99.8% of the mass of the solar system, is only a quarter. That means that most of the solar system is empty space. And then we have like these grains of salt that are orbiting a quarter, and we live on that grain of salt. We, as humans, are all living our life, all 7+ billion of us, on a grain of salt that's orbiting a quarter. How far away are we orbiting? So let's take a look, and then I'm going to show something else that I worked on right before this. So here is a generic picture of a football field. I've put the sun at yard line 0, Neptune all the way out here at 100 yards. So let's see where the planets fall. To answer our question first, the Earth would be at the 3.3 yard line, parked right next to the sun. In fact, all the terrestrial planets, the planets that have surfaces, rocky surfaces that you could jump up and down on, Mercury, Venus, Earth, and Mars, are all within the first 5 yards. So we have basically a grain of flour and 3 grains of salt scattered in the first 5 yards. Mercury at the 1.3 yard line, Venus at 2.3, and Mars at the 5 yard line. Then we have to really start hoofing it to start getting to the farther away planets. We have Jupiter, our biggest planet, and a gas giant planet at the 17.3 yard line. We have Saturn at the 31.7 yard line. We have Uranus at the 64 yard line, and yes, you pronounce it Uranus. Do not pronounce it the other way. Well, you're free to pronounce things however you want. I will pronounce it the correct way, which is Uranus. So there's our scale model of the solar system. Are you a little bit surprised? Are you amazed by how much empty space there is? Are you amazed at how small the Earth is? How small actually the sun is on this scale? So far, we've really only talked about one star. We know there are other stars. You can go out on a clear night and see plenty of them in the sky. On this scale, how far away is our closest neighboring star, Proxima Centauri? It has a real distance of 4.24 light years, which means a beam of light traveling at the speed of light, the fastest that anything can travel, takes 4.24 years to reach us here at Earth. That's about 25 trillion miles. Trillion with a T. The number's there on the screen. So on this scale, if we were in person, I would probably have you all discuss where you think you'd have to go to find it. But let's just go ahead and give up the ghost. On this scale, we would find our next quarter, our nearest neighboring star, and Proxima Centauri is right near Alpha Centauri, which is a star that's very, very, very similar to our sun. So another quarter, it would be in Washington, D.C. So go to the National Mall, drop another quarter there, and that's where our nearest neighboring star would be, Washington, D.C. What's between us and DC? Empty space. A whole bunch of nothing. Whew, this is starting to get a little mind-blowing. Okay. So we know that we live in a galaxy called the Milky Way, and there are other galaxies in the universe. Our nearest neighboring galaxy, the Andromeda Galaxy, is 2.5 million light years away. That means that the light that's leaving all the stars of the Andromeda Galaxy takes 2.5 million years to get here. So whenever we see it, we actually see as it was 2.5 million years ago. On this scale, if the solar system was squeezed down into a football field, so that the sun would be a quarter of the 0 yard line and Neptune would be something like half of a pinhead, all the way out at the 100 yard line, where would we put our nearest neighboring galaxy, the Andromeda Galaxy. And for this one, even on the scale model, I would have to run to my garage, grab my handy dandy spaceship that I keep there, take off, fly all the way to the sun, realize that I forgot something important, turn around, fly back to Earth, pick up what I forgot, and then I would have to fly halfway back to the sun again, or I'd have to fly all the way back to the sun again just to reach or travel the distance to reach the nearest neighboring galaxy, the Andromeda Galaxy. That is a lot of distance. Wow. That would get me out into the asteroid belt if I was leaving the sun. It wouldn't even get me to Jupiter if I was leaving Earth. Okay. Take a moment, recenter ourselves. We have now talked about two stars. Our sun being one of the stars that make up the Milky Way galaxy. I highly encourage everybody at some point in their life to go out to find a nice dark sky site. I was out on the 17th of this month, so just a few days ago. I went up to Cades Cove. It was a crystal clear night on a new moon, and I took this image of the Milky Way galaxy, where all the stars are so close together that we can't see them as individual stars, so we get this milky sort of path through the sky, and then dust lanes that block it. So we know that we're just one star in this artist's conception of the Milky Way galaxy. So the next question that you're going to answer on the Google form is, what is your best guess to how many stars are there in the Milky Way galaxy? This is a big question. Just take your best guess. And again, go ahead and hit pause on the video, put in your best guess on the Google form, and when you're done, come back and you will find your answer. Brief pause. Okay, enough silliness. So the answer, our best estimate for number of stars in the Milky Way galaxy, one galaxy in our universe, is 100 to 400 billion stars. The real answer is converging closer to 400 billion stars. So you can see that number written out right there on the slides. Billions of stars, hundreds of billions of stars, just in our Milky Way galaxy. And how far away Alpha Centauri is not that far off from the average distance between the stars, so you can get an idea of the distribution. They're just little coins separated by vast distances, hundreds of miles, if we were to scale the solar system down to fit on a football field. All right, let's go even bigger. Let's go a little bit more mind-blowing. So the Milky Way galaxy is just one galaxy in the entire observable universe. The Hubble Space Telescope picked a dark patch of the sky and stared at it and just collected light for a ridiculously long amount of time, where they thought there was relatively empty space. This is the image that they saw, where pretty much everything in this picture, what's called the Hubble Extreme Deep Field, is a galaxy. So we know there are a lot of galaxies in the observable universe. My question to you and the next Google form question is, how many galaxies do you think exist? What is our best estimate for the number of galaxies and your best guess for the number of galaxies in our observable universe? Just the universe that we can see. There's certainly more universe past what we can observe. So again, hit pause on that Google form. Go ahead and put your answer in. Don't submit the form yet. Don't go back and change it after you see the answer. And when you come back, you will be surprised by the answer. And now to the answer. So the answer to the number of galaxies in our observable universe, where the Milky Way is just one of them, is roughly 1 to 2 trillion galaxies in the observable universe. Trillion with a T, one with 12 zeros after it. And each one of those galaxies is containing tens to hundreds of billions of stars. Some of the largest galaxies even contain trillions of stars. That is a lot of stars in the universe. In fact, if I just do a quick estimation here, there are about 100 billion stars in the Milky Way galaxy, and there are about 1 trillion galaxies, Milky Way-like galaxies, out there in the observable universe. I can get an estimate for the total number of stars in the universe, and it is this enormous number right here. That's a 1 with 23 zeros, or 10 to the 23 stars. That is an absurdly large number of stars that exist out there in our observable universe. In fact, that is more stars than there are entire grains of sands on all of Earth's beaches. An incredibly enormous number of stars. And what is even more amazing is over the past few decades, really over the last decade, we have had satellites that are out there looking for planets around other stars. We have discovered thousands of them. Planets in orbit around other stars, so-called extrasolar planets. We've discovered enough of them where we can bring statistics to start understanding how many of each type of planet there are. And we know that there are at least as many planets as there are stars in the universe. That's not saying that every star has a planetary system. Some stars have no planets, some stars have multiple planets. Heck, we've got 8. But out of all the planets that are out there, it's looking like 1 out of 6 are Earth-like terrestrial planets. Sure, they're not exactly Earth-like. They might be more Mercury-like, they might be more Venus-like, they might be more Mars-like. When we say Earth-like, we're just saying terrestrial. They might be in the habitable zone, they might not, but that's 17%. So how many Earths does that give us? Roughly about 10 to the 22 in the observable universe. How many of those are in the habitable zone? Here we have 1. Technically, we kind of have 3. So let's just drop it by another factor. That's 10 to the 21 stars. 10 to the 21 stars in the universe that have Earth-like planets in a habitable zone. How many of those have life? That's a much, much harder question. But with numbers that large, for me personally, it's really, really hard to imagine that we might be the only life in a universe so abound with planets. I really hope that you've enjoyed this exercise. You feel free to pause and read what I have on the screen. If you're in Astronomy 151, I apologize. I want to do a common set of slides. So just imagine this is Astronomy 151. The lesson today is the same, but I hope this gives you a little bit of perspective of how incredibly large our universe is. I hope this has been a slightly mind-blowing experience. And most of all, I want to welcome you to our semester of astronomy. I really do hope you enjoy it. Thank you for paying attention and listening, and I look forward to seeing the responses on Google.